Hey guys, it's me again with a new normal stress problem. Let's go and analyze. It says here we have a 1,000 kilogram uniform bar, AB, which is suspended or being held by two cables, AC and BD. And each of these cables have the same area, which is 400 millimeters squared. We need to find the magnitude of P and also the location of X. And the stresses of each of these cables are AC 100 megapascals, and for BD is only 50 megapascals. So let's start with the cables. Since we are given an area of the cables which is 400 millimeters, and we are also given the stresses of each of these cables, we can solve for its force. So let's solve the force of each cables. Remember that the formula for stress is Q force over A. Since we are missing P, we'll just cross multiply, and that gives us QPA. There you go. Substitute the values. I think that's 40,000 newtons because multiplied by m squared just cancels it out, leave newtons. Now for PdB, you get 20,000 newtons. There, we've solved all we need from each of these cables. And since these are positives, we can conclude that these forces go upwards. Which makes sense because if they both go downwards, they'll crash. There you go. Next step. Now we need to find the P in relation to the bar. So how do we do that? Well, we have the forces already of each cable, which goes upwards. We are also given a value of the weight, which is just 1,000 kilograms. Now we can't use that yet, so we have to use it into we had to convert it into a usable force. And to do that, we multiply the weight with gravity. So basically, it's just 1,000 kilograms multiplied by 9.81 ms squared. And that's about 9,810 newtons because kilograms multiplied by ms squared is just newtons. So we finally have a usable load, which is 910 newtons. We have a lot of we have a lot of vertical loads, and P itself is a vertical load. Therefore, we could just use the summation of all these vertical loads to get P. So, summation of all these vertical loads We have 40,000. We have negative p because it goes downwards. We also have negative the gravity because it also goes downwards unless something happens and to change that. Some world breaking stuffs. Now, of course, for the second cable, which is 20,000 newtons, 0 isolate P. To isolate P, we just transpose P. And then just simplify 50,000 on 190 newtons. There you go, we found P. Now we need to find X. And since X is just a length, we can use moment because moment tackles lengths as well. Remember whenever we moment, it kind of goes like this. Now we could moment at B, but I'm gonna moment at A. That way it becomes like this. Ah, yeah, because it's simpler. If we moment at B, we'll be getting something like this. Yeah, which is kind of complicated, so to make things less complicated, we'll moment at A. So let's moment at A. Measure a moment at A equals 0. Now that reduced this because this is where we are momenting. Let's get all the values. What is P? P rotates clockwise in relation to A, so that's a negative value. Same with gravity. That's also a negative value, but let's not forget the distance of P from A. It's just 1 meter. This goes upwards, so it's positive. I mean, it's not positive because it goes upwards. It's positive because it rotates counterclockwise in relation to A. So that'll be 20,000, I think. Yeah, 20,000 newtons. And its length will be 2 meters away from A. Equates to 0. Now, just to clarify, the reason why counterclockwise is positive and clockwise is negative because it's it represents the thumb rule. Most people also do, but I know some school teach it the opposite way, where counterclockwise is negative and clockwise is positive. It could work either way, I think, but this is usually how it's done because it directly follows the thumb rule. Now, let's go and isolate x. Let's just transpose it. It'll become a positive value of n x, leaving these the same. 9, 8, 10 plus 20,000, 30,190. 30,190 n dot m. Now we isolate x. It just brings down this one. cancel like terms, solve. That'll give us 0.602401, but it's 02 meters. We have found X. So it's like somewhere here. Very, very thin, I think. There you go.